Quiero agradecerles por su presencia aquí en esta mañana, en este seminario internacional de las tecnologías más avanzadas que hay en mezclas asfálticas en el mundo en este momento. Nos sentimos muy honrados de ver a todos los que están participando hoy. Es parte del trabajo que hacemos nosotros en el LanammeUCR, de las actividades de transferencia tecnológica que hacemos como universidad primero, pero también por los fondos que nos da la ley 8114 para transferir tecnología en el país y en la región centroamericana. Tres de los objetivos de la ley 8114 tienen que ver precisamente con la transferencia de tecnología y por eso es muy bueno poder aprovechar esa coyuntura única que da en Costa Rica, tener financiamiento, tener fondos para poder hacer eventos de este tipo, sin trasladarle todo el costo a los participantes, sino que sea subvencionado por la ley que nos da fondos. Entonces estamos muy contentos de verles aquí. Este seminario es un seminario muy especial por los expertos que estamos trayendo. Son profesionales, son científicos del área de pavimentos que han hecho investigación de primer nivel en el planeta. Son líderes en sus campos, en sus universidades y no solo a nivel de las regiones donde ellos están, sino a nivel mundial, que han marcado el derrotero que hemos seguido muchos de nosotros para poder llegar a la tecnología que tenemos hoy día en materia de diseño de mezclas asfálticas, que es muy nueva comparado con lo que todavía rige en la región latinoamericana, que como ustedes saben es la tecnología Marshall, la tecnología del Ashton 93, que son tecnologías que estamos buscando cambiar nosotros en los últimos años y que ya en Costa Rica hemos venido liderando el cambio en la región latinoamericana, teniendo ahora nosotros especificaciones ya por grado de desempeño, especificaciones para asfaltos modificados y ya prácticamente una guía de diseño empírico-mecanicista con software preparada para Costa Rica, que por supuesto queremos que se aplique en la región centroamericana. Parte de la labor de nuestra universidad, de la Universidad de Costa Rica, es la transferencia de conocimiento también. No solo lo hacemos porque lo dice la ley 8114, primeramente lo hacemos porque eso lo dice el estatuto orgánico de nuestra universidad. Y estamos muy contentos por hacer esto. Este es prácticamente el último evento grande que tenemos en el año, todavía nos queda uno en un par de semanas de auditoría técnica y cerramos un buen año con muchas actividades de capacitación. Este año tuvimos unas 60 actividades de capacitación en recursos para técnicos de laboratorio, inspectores de campo, cursos de actualización profesional, en todos los campos del área de la ingeniería de pavimentos, desde los campos más administrativos de proyectos hasta los campos de la nanotecnología. Y bueno, muy contento de verles. La primera presentación que vamos a tener hoy la va a dar el doctor John Angelo. Tenemos también al doctor Gordon Eiry de la Universidad de Nottingham, sudafricano, que trabajó muchos años en CECIR, y también la doctora Joe Daniel de la Universidad de New Hampshire. Pero la primera presentación, que es a cargo del doctor John Angelo, va a hablar acerca de los ensayos de desempeño en la mezcla, va a hablar de diseño balanceado, que es un tema, debo nombrar que a través de la unidad de auditoría técnica hemos estado analizando profundamente, y la unidad de materiales y pavimentos, que es otro concepto de diseño de mezcla asfáltica. Vamos a hablar de materiales, control de calidad y ensayos. Si ven del doctor Angelo no tengo nada escrito de su trayectoria, no lo necesito, porque remontándome al año 1997, que fue cuando entré a trabajar a la NAME, y los primeros años cuando empecé a hacer armas en el laboratorio, y cuando fui coordinador del laboratorio de infraestructura vial allá del año 2001 al 2005, la mayor investigación que seguíamos nosotros era lo que el doctor Angelo estaba generando en aquellos tiempos cuando estaba a cargo de toda el área de materiales de Federal Highway Administration. El doctor Angelo tuvo a cargo buena parte del desarrollo y, el control del desarrollo del SHARP, el programa que todos hemos estudiado, el Strategic Highway Research Program, que decantó después en la especificación de grado de desempeño, el Performance Grade que todos conocemos, y también el método de diseño de mezclas SuperPave. Trabajó mucho en investigaciones, por ejemplo, en el tema de polímeros para determinar temperaturas de mezclado, compactación, los ensayos ideales, y uno de los últimos desarrollos que ha generado y que está tomándose en buena parte del mundo, los que trabajamos con asfaltos modificados, es un famoso ensayo, el Massacre o el MSCR, que es un extraordinario ensayo para el desarrollo y el análisis de asfaltos modificados con polímero. Entonces, como verán, tenemos una persona que lideró un tema que hemos estudiado por muchos años aquí. No me dejan mentir los compañeros que tengo aquí que tienen más años de estar en el LanamME, como Mónica Jiménez o don Ernesto Villegas, que están por ahí. Cuando nosotros empezamos a jugar con los reómetros, empezamos a jugar con el compactador giratorio de SuperPave, allá por el 99-2000, estudiamos mucho de lo que el doctor de Angelo desarrolló en aquella época y lo que ha desarrollado todos esos años. Todavía el doctor de Angelo sigue siendo un líder muy importante en muchos comités de investigación, tanto dentro como fuera de Estados Unidos, y en todos los grandes eventos del planeta generalmente está involucrado. Entonces es realmente un honor tenerle aquí con nosotros al doctor Don de Angelo. Doctor, it's a pleasure to have you here. Vamos a recibirlo con un fuerte aplauso.
Thank you very much. A great pleasure to be here. First time to Costa Rica for me. It's a rather lovely country, and I've known the professor for quite a few years and talked to him, and we've had discussions, and he always tells me about how wonderful it is here, and now I have the opportunity to see that he was really telling the truth, and it is a great place. What I want to talk to you about today is something that is growing pretty much worldwide, and it's the idea of what we call performance mixed design. And so people say, well, what's performance mixed design? We always design for performance, right? We don't design for just for the sake of it. We want performance. But the question comes about, how do you really tie those performance characteristics you want to the materials you have to use? Because we know we all have experience. We mix aggregate with bitumen. We have old formulas that we've used. Sometimes they worked, sometimes they don't work. Well, now with the tremendous increases of traffic, we have to maybe take the next step, be a little bit more sophisticated in how we try to combine these materials to get better performance. And that's really what we're going to talk about today, is some of the new tools that are being used to try to optimize how we put this aggregate and bitumen together to get the performance characteristics we really want on the roadway. So really that's what I'm going to go over in a number of slides, and hopefully you'll have a copy of these slides later to go back and review and go over. I don't know, are you going to provide copies? Yeah, okay, thank you. And I think they're going to be translated, so it'll be easier for you to to go back and review them also, so that'll be good. But we're going to go over what the concept of basically performance design or balanced mixed design is. We'll review the performance tests that are being considered, in this case mostly in the US, but also other places in the Middle East now. I do a lot of work, and we're also using a lot of the same performance tests. We're going to understand how there is an interrelationship between our older type of mixed designs, things like Marshall and SuperPave, which use the volumetric properties, the air voids and the VMA. Those don't go away. They're still relatively important, but maybe we can make adjustments to that. Then we'll talk about, how do you do this testing? And then most importantly is, how do you make sure that when you build the road that you're getting what you want? That's very, very important. So when we look at this, new idea of performance mix design, we have to go back and look at the old specifications. What do we have? There are many different ones that were available. We have method specifications, and that's where you write down in detail exactly what the contractor is supposed to do. You tell, I want to take this percentage of aggregate, this percentage of bitumen, at this temperature, you mix it, you place it on the roadway, you make so many roller passes, and basically the contractor does what's in the specification, or hopefully he does what's in the specification. Not always. We all know that sometimes things don't always work out exactly the way they're supposed to, but with these type of specifications, the government, the agency, assumes all responsibility. If you tell the contractor exactly what to do and how to do it, and he says, that's what I did. If the pavement fails, he says, I did what you said. Don't look at me. So over the years, we've been transforming from that method specification. And now even in the US, we still have some old method specs for certain things that don't change. But for the most part, we've moved away. Now, the next one that's being used quite a bit now is what we call quality, this QA, QC, which is quality assurance and quality control. And that's where you turn over responsibility to the contractor to do the testing, to control the product, to make sure he's consistent, that he's combining the materials the way he's supposed to, and then the agency does testing on the finished product to look at acceptance, to say that, yes, what he did matches what we wanted. But then you have the next part, which is what we call performance-related specifications. And that's where we're really going to talk today, because we're going to talk about performance characteristics, performance tests that we tie to those materials that we combine together, the asphalt mixtures and the placement on the roadway, to actual performance and of the characteristics that we want. The other specifications, we won't cover them today, but just to let you know, there's things like warranties, where the contractor builds the road and he tells you, I will be responsible for this road for 5 years, 10 years, and if anything happens, I have to fix it within certain contractual limitations. There's always limitations. You can't just say it's yours. And then there's actually performance specifications, and that's where you just say, I want no ruts, no cracking, and you have relationships. But we're really going to talk about what our performance design is, performance-related specifications. So what are we really talking about when we say performance-related specifications? They're driven by key indicators. Those are these things that, like we say, what do we expect for rutting? What do we expect for cracking? But you also have to realize in the construction world, there's variability. I can design a mixture in the laboratory. I can take one rock and this rock, and I can combine them together and have an exact formulation, and I put exactly the right amount of bitumen, and then I test it and I look at the properties of that. But in the real world, there's variability. Now I'm combining tons of aggregate with tons of bitumen in an asphalt plant. And there's variability in those materials. That I don't control every single rock. And then I transport it to the roadway, and it gets dumped in a truck, and it gets dumped into the hopper of a paver. And each one of these things makes changes and variations in that mixture, and then it gets placed on the road. So you have to also take into account these variations and say that I can accept variations within a certain limit. And that with that variation is going to be also variations in my test results. Because if I don't accept that, I will be very unhappy, because I know that in the real world there is variability. We're all variable, right? We all look different. We're all people, but you look different than you, and that's we like that. And humans, we like all that variability. But on a roadway, we like to minimize it. We like to keep it as small as possible. But it is there, and we have to accept it, and we have to take that into account. So one of the key things that we have to look at when we're trying to set these things up is that it's critical that you identify the problem you're trying to solve. Because if you don't ask the right questions, you can never really get to the heart of your problem. And I like this, I found some pictures that I like. So the first question you see here, okay, you have a truck. It's got a big rock in it, and it looks like the truck is broken. All right? So the question I have, is the rock too big, or is the truck too small? It's a simple question, but the answer is going to be very, very different depending on which question you have. Because if I want this rock big, and the rock is too large, but I have to move it, well, what do I do? Actually, if the rock is too large, and I want to make it, and I need to make it smaller, well, what do I do? Well, I have a crushing facility. I can make the rock small, and then I can put it in the truck, no problem, right? I can make a lot of small rocks. But if I want the big rock, I don't want to crush it. What do? I have to get a bigger truck. But you can see, I have a rock and a broken truck, but depending on what solution I want, I have very different directions to go in. So it's the same we have to look at in our testing on the roadways. We have to ask the right questions. We have to really understand what results we want so that we can then go into that direction that's needed. So let me start then. What do we talk about when we talk about balanced mix design, which is all part of this performance-based mix design? And we want balance in this design. Well, what is balance in the design? Well, we want to use performance testing related to the appropriate conditions we're dealing with. In other words, is my design the same for every single roadway? Of course not. If I have a small local road with just light traffic, I have certain different design criteria. But if I have a very, very, high traffic roadway with a lot of trucks, heavy loads, I'm going to have different design criteria. And so we have to take that into account. We also have to take into account aging. And as you get older like me, I don't see a lot of gray hair in here, but I got a lot of gray hair. And I have to take into account aging. In my life, I have to look at, maybe it takes me longer to do things than it used to. Maybe there's a little bit more creaks when I move. Well, that happens to a roadway also. When I mix that aggregate and bitumen together, when it's new, it looks black, it's flexible, it goes down on the roadway. But as it ages, it changes. And the properties change. And how it's going to react to traffic and the environment will change with age. And we have to take that into consideration in our design processes. And so that's part of, some of the testing we look at is how do we make adjustments to that, those materials, so that we can have that road that will perform even later on in life as it ages. We want good proper performance, not for just today, but we want it for tomorrow and next year and the year after that. So we have to take that into account into this whole idea of balanced mix design. So again, you want to have the right mixture with the right materials for the right job. This was a little bit hard to see, but it's really something you all know. It's just sort of a history of mix design. Back in the about 1900, there was the Barber Green Asphalt Paving Company, and they really had what we call methods, we mentioned earlier, a method specification where they took very certain amounts of stone, aggregate, and mixed it specifically with at bitumen, and they patented that. And so anybody who wanted to use that formula, they had to pay a little bit to the Barber Asphalt Company, but it was something that was used on a regular basis. Then there were some changes. People came out with new patents, new approaches, but very, very similar, where you would, combine aggregate and bitumen together to have certain types of characteristics, and that would go down. Then, back in the, early 1900s, it was Hubbard came up and said, we can't just have a pure formula, two shovels of stone, one shovel of sand, one bucket of bitumen. It doesn't really work. You're going to have to be a little bit more sophisticated. And so they came up with a test to blend the aggregate and bitumen together, and they had a compression tester, and it was just a ram, very similar to like you see a soil test, and they would apply pressure to that and see how much it should indent it into a specimen, and that was called the Hubbard field method. Then probably something more that you're more familiar with is the Francis Veeam and the Veeam mix design, and that used this very specific compaction device. It was a kneading compactor, and there was a little arm that came down and pressed into a mold and twisted, and then the mold turned, and the thing went up and down, and they compacted the mixtures in the mold, and they looked at certain characteristics of that mixture. They had some tests that they thought were related to performance. It was the Veeam stabilometer and the cohesiometer tests that they said, well, this will tell us if the mix is going to perform. And that was used very predominantly, mostly on the west coast of the U.S. Then there was Bruce Marshall, which was the Marshall mix design, was in the late 30s. Again, the same concept. He had a little mold and a hammer that would compact the aggregate and bitumen in the mold, and then he would look at certain properties of that mixture, usually the Veeam stability and the flow number. And that actually was and it probably still is the most predominant design system in the world. And it's interesting how this happened. People say, well, how did Marshall, this guy from Mississippi in the U.S., get his mix design system all over the world? Well, he used to do a lot of work for the Army Corps of Engineers. And the Army Corps of Engineers adopted this Marshall mix design because the Vicksburg Research Laboratory for the Army Corps of Engineers is right there in Mississippi, right, and very close to the Mississippi Department of Transportation, and they adopted this. And they adopted this mix design for the process of doing airfield pavements for the military. And what happened in World War II? The U.S. military built airfields all over the world, literally all over the world. And after the war, people were trying to rebuild the world after it fell apart, and now they had this Marshall mix design. And it sort of just spread from there. And that's really how it all spread. It was actually from World War II and the U.S. military building airfields everywhere, this Marshall mix design. And it's not a bad mix design system. Almost any mix design system, once you understand the materials and the nuances of it, you can make work. But we were having problems in the U.S., so we were looking for something different. We wanted some way to evaluate new materials and new processes and not be confined to a limited approach where you sort of had to understand the exact materials you had, and it was not very open to to evaluate new materials like polymers or maybe some new types of gradations. If you notice in most Marshall designs, it's a very narrow gradation band because people have experience with those bands and they seem to work, so that's okay. But now if we get outside those narrow gradation bands, we don't know if the Marshall system will work. So you have to go back and do field trials, and it gets to be laborious. And so it's not very open to change. It's very, very difficult to move things forward. So we looked for something that was just super paved, which then had different criteria, a different compaction system, that we hope would simulate the real world a little bit better than the Marshall. But it still had some problems. It didn't have the final performance tests. But now a lot more of those tests have been developed and are evolving, and that's really what we're going to start to go over for the rest of this. So why do we need balanced mix design? Why can't we just stay with the same criteria we have? Well, what happens? We've seen, especially when we adopted the SuperPave system in the U.S., all of a sudden, before SuperPave, we had a lot of rutting. There was a tremendous amount of rutting throughout the U.S., and that's really why it was the impetus to make a change. How do we get rid of all this rutting? And so the SuperPave design system was developed, and it was adopted over a number of years by the highway agencies, so now it's just about every single highway agency in the U.S. is used exclusively. But what we've noticed over the years now that the mixes have become dry, and there's a lot more cracking. And so we made the transition. We eliminated rutting, but now we're starting to have cracking. Now, we also realize that, okay, if you want to stop cracking, we can put more bitumen in, correct? Sure, we'll put more bitumen, we'll have less cracking. However, we don't want to go back to the problem of rutting. And that's been a typical thing throughout the years. You have rutting problems, you take the bitumen out, then you have cracking problems. Then you go back, you put the bitumen back in, and you have rutting. But we were saying, how do we now look at this so that we can address both rutting and cracking, optimize those materials so that we can get overall good performance with minimized cracking and minimized rutting. And that's really the common, why we're looking for balanced mix design, to try to find the formulations that we can optimize to give us performance in both areas, and develop specifications to do that. So this is just an old slide looking at, this whole process. And if we look at this, we see here that with low bitumen, okay, we have high stability, okay, but we may have poor durability because there's not enough bitumen. We have, raveling. Now, as we increase the bitumen, the stability sort of peaks, but then it drops off after a while, and we get rutting. But now the durability goes up. We have no cracking and raveling. So we have to figure, how do we find this spot in the middle where we can optimize both the cracking and the rutting, the durability of what's going on in the mixtures? And we had hoped that volumetrics and proper compaction would address that, and it does help a lot. But it doesn't answer all the questions. And again, it doesn't give us an opportunity to evaluate new materials quite as easily. Because, again, if we have the old systems, we're not sure exactly when we're in this middle. If we're just looking at things like stability and flow, because if you change the gradation slightly, stability and flow can change tremendously, but you can still get good performance. And we've seen that in many places around the world. So this, there were some, surveys that were done asking highway agencies, what are your primary problems? And one of the largest problems that was identified is cracking. Longitudinal cracking was a large problem. Reflective cracking, some raveling, thermal cracking. There's slippage problems, which is a construction problem. This is where the one layer is not bonded to another. Fatigue cracking, and then top-down cracking. And you've noticed in the U.S. now, this was a survey by Old Castle Construction to some of their different plants around the country with the problems. Rutting is not one of them. So again, we've eliminated a lot of rutting. Now it's a cracking problem. So we've got to combine that. They also looked at what are highway agencies that they recognized that this was a problem was trying to do. Well, a lot of agencies in the SuperPave design system, you have so many gyrations of that mold as you're applying pressure, and you're hoping that that compaction effort. As you put more compactive effort, that should resist cracking. But it also has a tendency then to take out asphalt out of the mixtures. So highway agencies have started to reduce the number of gyrations they put on them. Well, just similar to the Marshall hammer, maybe I put less blows. You know, I have a 50 blow or a 75 blow. Maybe if I do a 60 blow in the middle, it'll be optimized. Same thing with the gyratory hammer. But, you know, and that was the concept is that, well, maybe I can get more bitumen into the mixtures by doing that. But it doesn't always work. You know, if you don't control the gradation, the gradations can be readjusted so that you're, again, always at the minimum bitumen content. And the contractor, and you can't fault them for this because this is how they can do business, they have to design a mix. They have to give you a mix with the minimum amount of bitumen in it. They have to. Because they work in a competitive market. They have to bid on a job. They have to tell you how much it'll cost them to put it down, and they want to get paid for it. Well, what's the most expensive item in an asphalt mixture? It's the bitumen. So if I'm going to save costs, what am I going to do it? I'm going to do it on the bitumen. I have to give you the minimum amount of bitumen that would still meet your specifications and your requirements. So I have to optimize for that. So we have to come up with systems to say, all right, what is that bitumen content now that is going to give us the properties we want? And again, that's the whole concept of the balanced mix design. And, you know, but we know bitumen is a key item. There's been studies that, you know, what is a key concept in enhancing durability. And, you know, this was done by the National Cooperative Highway Research Program in the U.S., part of the Transportation Research Board. And what they came up with was that, I keep doing that, is what's the effective binder volume, or the respective binder volume, which is the VMA minus the air voids. Now, you notice the key word here is volume. It is not percent binder by weight of aggregate. That is something that most people that do mix designs get lost in and make mistakes about. You think if I have higher percent binder by weight of aggregate, it's good. And I try to relate that percent binder in the mix to performance, but it's not the weight, it's the volume. Because if I have a very hard, dense stone that I want a certain volume of binder, my percent by weight is going to go down, even though I could have actually more volume of binder in it, because it's a percentage by weight. So, but the volume is a consistent property, and that's this whole mix design. If you go back to MS2, the manual, and you look at why do we design the mixtures for air voids and VMA and then tie to stability, and we just pick whatever that optimum, because it's the volume of materials, the volume of stone, and the volume of bitumen when compacted into a specimen that count. And that's a key item to remember. It's always the volume. So, and when you want to make analysis of things like performance, you go back and you look at this effective volume of bitumen. And why effective? Well, and I can tell by the geology here, you probably have a lot of stones that have relatively high absorption. And so as you make a mixture, that bitumen gets absorbed into the stone. Now, it's important. You have to do that because that stone is going to suck it up, and you have to account for that, and that's important in the whole weight. But when you look at the volume, you subtract out that bitumen that gets absorbed, because now it's not working as a lubricant between the stone. It's just part of the process that had to be absorbed. So it's important to look at that aspect. Now, so agencies are searching for solutions to these problems and how to improve durability. And so what are they looking at? How are they doing some of these things? They're changing the bitumen grade they have to stiffer materials, more polymers, more elastic. They're lowering the number of gyrations in the Marshall in the gyratory to get more asphalt. And there's all kinds of different approaches here, and I'm not going to go over the details of the lowering the amount of recycled pavement that we use. Do you use a lot of recycled pavements here? Okay. Well, in the U.S., we use a tremendous amount of recycled pavement, trying to conserve the aggregate and some of the bitumen. But that'll affect your overall durability because now you're putting the aged bitumen back into the mixture. So there's, and then we're looking at performance testings for cracking, increasing the VMA in the mixtures, all to try to get more bitumen. There's a lot of different approaches, but the number one thing that we're trying to look at now is actual performance testers on the mix to try to optimize those properties that we want that'll give us good performance. So, what are some of the common things that we're looking at for balanced mix design? Well, to do that, we have to go back and, what type of distress are we having here? Well, there's moisture damage, and I have noticed driving around, you do have some issues with moisture damage, where, basically when the mixture in the roadway is, exposed to significant amounts of water, and you have a tropical climate here. It rains a lot. You actually can dislodge the bitumen from the surface of that stone, and next thing you know, it looks like gravel. I say, what happened? Why is my road, just gravel? The other one is rutting. Rutting's a big problem. We had it in the U.S. We still have some here, and again, that's that balance. If I put more bitumen in, I could have maybe less problems with moisture damage, but now I have rutting. The other one's cracking. If I have fatigue cracking here, a lot of bottom-up cracking, that's where it's relatively a dry mix, or it could also be an indication of a thin pavement structure. Maybe my thickness of my pavement is not enough, where you start looking at, maybe I needed greater thicknesses. Thermal cracking here. Now you say, oh, you're never cold here. You can have thermal cracks, but it never freezes. Because as that bitumen ages in the pavement, and if the pavement is very, very old, it becomes brittle. So even at higher temperatures, you can get cracking. And we see this, very often. It doesn't necessarily always show up as a transverse crack all the way across the pavement. It actually sort of appears more as block cracking. You see when the pavement breaks up, the cracks form into blocks, maybe 1 meter by a meter in the sort of squares. But that's actually a form of thermal cracking that establishes as that bitumen ages, and it wants to get brittle, it wants to contract, and it can't. We also have problems with reflective cracking, where you have cracks from an old pavement below that go right up through the new pavement. And then we have one that's sort of a newer problem it's developed a lot, is what we call top-down cracking. That's these longitudinal cracks right along the edge of the tire. And we see that mostly with thicker pavements that have lower bitumen contents. And so we have high stresses developing right at the edge of that tire on heavy loads, and it forms longitudinal cracks down the wheel paths. So there's some of the things that we see. I'm probably going to just quickly say on this slide, highway agencies, are all looking, a number of them are looking at different mechanisms. And the only thing I would say important here, the biggest item that most highway agencies are looking at is this fatigue cracking. You see most of the highway agencies in the U.S. want to address some kind of fatigue more than anything else. Okay, but they also want to look at rutting to make sure that they don't take away the fatigue cracking problem, but create rutting problems. So they try to balance those, and that's, again, balanced mix design. So when we look at that, there's a lot of tests that we can do because we want to be able to tie the performance testing to the distress we're talking about. So it could very well be, you have an area with, extremely heavy loads. Okay, and that's just, this is just an old picture from 1947, of logging in the northwest U.S., where they used to cut down the giant redwood trees, and these trees would be, 3 meters in diameter. 3 or 4 meters of giant trees, and they would put them on trucks and ute cars probably, or even the modern day logging, adds up to pretty significant load on the road. So you have to be able to address it. So there's a lot of different tests that are being looked at, some that you're probably familiar with, some maybe that you're not so familiar with. You know, we have the Homburg wheel tracking test. That was one that was developed in Europe, probably about 25, 30 years ago. But it's a very effective test to look at, you know, the running of mixtures. Another one is the asphalt pavement analyzer. It was something that was developed in the U.S. Sort of, just again, it's just a wheel tracking test. And then something that's maybe a little bit more fundamental, looking at rutting, is, you know, the flow number test and the dynamic modules. And that's where we put repeated loads on an axial specimen and very accurately look at the strain that develops based on the controlled loading that we put on. And so these are the things that we look at for, you know, being looked at for rutting. Then we can have durability, you know, cracking, and there's a lot of different tests. And this is what makes this part the most difficult one to address, because when we look at cracking, there are many different kinds of cracks. And the distress, or the loading that causes those cracks, causes that distress, varies. So there's no one test that can address all types of cracking. So you have to sort of, again, ask that right question. What is my problem? What type of cracking do I have? What type of cracking am I trying to solve? And that's going to relate to the type of testing that you would do to address that, whether it's durability, things like fatigue cracking that we see here, or is it, you know, block cracking or transverse cracking, and this is, you know, the old thermal cracking across the roadway. So we have a lot of different tests to look at that, and I'll go over some of these. You know, we have, in this case, this is a compact shaped disc tension test. It's this one right here. Here is a semicircular bend test. This is a beam fatigue. Here is an indirect tensile test. So there's a lot of different approaches, and they all give you slightly different answers to the problems. And again, you have to tie that to the type of the distress you're looking at. You know, what am I looking at? You know, am I looking at fatigue cracking because my pavement is too thin and I have a lot of load, or is actually it's not flexible enough? The pavement's inflexible, so I have a deflection, but it still cracks from bottom up. Or is it, you know, top-down cracking that I have here, or is it some kind of thermal cracking? And again, you know, the test you pick is going to be important to answering that, because if you pick the wrong one, it won't address your concerns. You know, so a lot of the things that we're looking at, you know, for fatigue or bottom-up cracking, we're looking at basically the beam fatigue test for one. Another test that's being used quite a bit, it's a little bit more empirical, is the Texas overlay test. It's a little bit easier to deal with. I'll go over exactly how some of these work in a little bit. You know, here is the semicircular bend test, which we take a specimen, you put a notch, and you apply a load, and you watch how it cracks. And then here is the axial fatigue test. It's actually similar to this test, but now instead of just putting a beam and bending it, I actually pull on the specimen and measure the response of that specimen. You know, for low temperature cracking, you know, this is the indirect tensile test. It can be done at low temperature, but there's also a version of this test done at intermediate temperatures. It's a new test that was developed in Texas. Here's a thermally stress restrained specimen test where we take a beam of asphalt and we actually cool it down and hold the end so that it can't contract, and we watch how that beam shrinks and it cracks. Here's a semicircular bend test for low temperatures, and again, here's a DCT, again, also at low temperatures, not at intermediate temperatures. So there's several different tests that can be done at different temperatures, and they'll provide different types of results depending on, you know, what you're looking for. Reflective cracking, again, same tests, but here, you know, you might do it at a different temperature or a little bit different loading rate to address the different types of cracking that you're trying to look at. And I'll show you some examples where you don't always get the exact same number from the tests. For this is the iFit test, was developed in the University of Illinois, and it's a fracture test. It's done at intermediate temperatures, about 25 C typically, and they take a specimen of mixture that's been compacted, a cylindrical specimen. They cut it in half. It's about 50 millimeters wide. It can vary though. They put a small notch in the bottom here so that you know that the crack is going to start at that particular point. They apply a load to it, and they look at how the specimen deforms and then cracks. Here you have your peak load where your crack starts to develop in the specimen, but then they also look after your crack develops, how quickly does that crack then propagate up through the specimen? Because the other concept here is that, well, I can have a mixture that's very resistant to cracking, and so I could have a very high peak load, but after that initial crack started, it cracks right through the pavement quickly, or is the mix still flexible enough so that even though I have that initial crack, I still have some flexibility in the mixture, and so that it doesn't have complete failure immediately. And that's sort of what this iFit test is looking at. So we have, several different tests depending on, they can be used at different types of conditions to look at these different cracking mechanisms to see how they work. And you have to, maybe run more than one test to really address all the different issues. So I'll show you this one. This is some work I was doing on recycled pavement. And what you see here is 3 different mixtures. The red mixture, that was an original job mix formula that the contractor had developed for a mixture with absolutely no recycled pavement in it. And then we developed 2 additional mixtures, one with 15% recycled binder in it, and that's the dark blue one. So you see here, this is the original one. This is dark blue one. It's a little bit coarser than the original job mix formula. And then when we had a mixture that we actually put in 38% recycled binder through RAP into that mixture. But you see here, that one is significantly coarser here compared to the original job mix formula, the low RAP mixture and then the high RAP mixture. And we did that because trying to get volumetric properties to meet requirements, because we had slight adjustments in gradation to get the recycled binder in there. And so in the end, what we were trying to keep the air voids similar, the VAMA similar, and the bitumen contents is, we reduced those slightly as we went along, but overall, we kept them. Now, the important thing to remember here, all right, if I look at you see here, the original job mix formula had by weight 5.4%, then the actual 15% recycled binder mixture ended up with about 5.2, and then when we went to 38% recycled binder, we actually had a bitumen content drop down to 5% by weight of aggregate, or by weight of mixture. But if we look at the VMA here, remember we talked about effective binder volume, all right? So if I subtract the 5.2 here from the 13.7, what do I get? I have 8.5. So that's my effective binder volume is 8.5%. But now here at 5%, I have 4.3. Oh wait, no, excuse me. I take the 4% from the 13. Okay, yeah, from the 7. I get 9.7 effective binder volume. But if I take the 4.3, even though I had a lower bitumen content, I take the 4.3 from the 14.9, and what do I have? I have 10.6. So even though I have a lower percent bitumen by weight, I have a higher binder volume, effective binder volume. And that's really what ties to performance. And I'll show you why that's important, because now as we're going to go through the performance test. So remember, the mixture with the higher percentage of recycled pavement and a little bit slightly lower percent bitumen by weight of mix actually has a higher binder volume. So again, this is 4 from the 13.9 leaves me 13.7 leaves me 9.7, and the 4.3 leaves me 10.3. So I have a higher binder volume. So if I look at, for example, this is the flow number test, and this is where we do the repeated load on an axial specimen and watch how that specimen deforms. And when it gets to a certain level, we call that the flow number. And we can see the mixtures with the low recycled binder, they actually have significantly lower flow number values. And why is that? Well, this is a softer material. If I put less recycled material in, the base asphalts are softer. So I have a little bit more rutting. But actually, these numbers are not bad. These numbers, this is about 500, and this one is about 350 flow number. They are acceptable for the level of traffic that we had on this roadway. But now when we went to the higher recycled binder ratios, and again, we had 2 different bitumens that we were using as virgin materials, you can see that now all of a sudden, these numbers jumped up tremendously. Now I have flow numbers that are, close to, 4,000 here, and this one is, almost 2,000. And part of that is because we now have a much stiffer bitumen. Now, the L bitumen here, it was a stiffer material. This was a PG 64 minus 22, and the H bitumen was actually a PG 58 minus 34. And why were we using this bitumen? Well, we wanted to put a lot more recycled binder into the mixture, and if I'm going to put a lot more recycled binder in, I try to use a softer base asphalt because I don't want to just address rutting. I also have to think about cracking. So you have to think about these materials you're putting in. So this is part of the evaluation. But we all basically saw that all of these are acceptable for rutting, but when we put the recycled binder material in, it increased the rutting up tremendously. Now, when we look at the Homburg wheel tracking, and this is important to note, same 2 mixes, or same 4 mixes actually. And what you're seeing here is that these 2 are the 15% recycled binder with the stiffer and the softer base. And here, the higher recycled things. But here you can see very, very minimal rutting for any of them. And so what this is telling me in this particular test is the Homburg wheel tracking test is much more sensitive to the aggregate structure. And the binders don't make that as big an effect. And that's the type of loading. You take specimens and you put a steel wheel on it and you run it back and forth, and they're confined, and the aggregate can't dilate or move sideways, as we say. And so that it tells us a little bit more about the aggregate structure, not as much about the binder. Where the flow number test gives us a combination of both binder properties and aggregate structure, but maybe it's a little bit more sensitive to the bitumen, type of bitumen, the volume and the stiffness of that material. So I'm not saying one is better than the other, because you're going to have different criteria. But you have to realize that, they're not always exactly the same. They'll show you slightly different numbers, and it's important. And basically, this slide just summarizes what I just said, so I can go to the next slide. Now, several other tests we ran on these particular mixtures. One was the flexibility index, and I mentioned that to you a little bit earlier. Now, this one was surprising until you think about exactly what was going on. So here are the mixtures with the lower amount of recycled material. So they're softer. And the higher the flexibility number, the more flexible the mix, the the less speed with which the crack will propagate. But as I told you, these mixes are actually softer. They have the softer binder, but we did age them. We put them in an oven and aged these mixes for 12 hours at 135 C, because cracking is an aging problem. So we wanted to see what would be happening with cracking after the mixture aged. And you can see here, you know, the softer binder, you know, is better than the one with the stiffer binder, but they both have the same amount of recycled material in it. But when we went to higher recycled ratios, we got better numbers. So you say to yourself, well, wait a minute, I put more recycled material in here. Why would I have better numbers? Well, let's go back. What did I tell you about this particular mixture? It also has a higher, it's a stiffer material, but it has a higher effective binder volume. So it's never just one thing. It's not just the stiffness of the material. You have to look at several different things. Now, if you just looked at percent bitumen, you'd be, this is crazy. It can't be right, because this actually has less percent by weight. But if you remember, the gradation was just slightly different. It was a little bit coarser, so you have some bigger stones, so the percent by bitumen to coat the bigger stones goes down, but the volume itself is up higher. And so actually it has better cracking properties, at least in this particular test. You can remember, you get a lot of different tests, and I'll show you some of them. Now, here is the Texas overlay test, and that's and I didn't cover that. With the Texas overlay test, we take that compacted specimen. It's again and that one is about 60 millimeters high and about 100, and it's 150 millimeter diameter specimen. So now you glue that down to 2 steel plates, and then you move one of the steel plates back and forth. It's so many applications per minute. And it's a relatively high strain test. It's not, you know, you're not tearing it apart, but you're doing that application, that test. And again, we see similar type of things here in this particular case, where the softer materials, you know, they have a certain number of cycles to failure, which are less than the cycles to failure on the stiffer mixtures. But again, if you notice, the softer binder with the higher wrap actually did outperform the stiffer binder with the high percent wrap, showing that there is a slight difference there. But again, it's a repeated load type testing. The differences aren't nearly as big here as we saw in the flow number test. So we see something, you know, so that you see slightly different results. But again, it's because of the effective binder volume. Now, I also mentioned the axial fatigue test, and that's where we take a tall cylindrical specimen, and we actually apply tension on that at very high frequencies, usually 10 hertz. And you pull on that specimen, you do it for, you know, thousands of applications. And you do that until it fails. And you do that at different strain levels. I might pull it at 800 microstrain, which is a large strains, and then I do it at a lower level of strain. And I look at, you know, how many of the applications do I have to failure, and so here's the strain that the testing's done at, here is the number of cycles to failure, and then I can get a plot of a curve here to look at how that mixture reacts to different strain levels in the pavement, and see, you know, which is better. Now, this particular mix, the farther you are up in this direction, that means at higher strains I can take more load applications to fail. It's better, all right? It's better because the more I can load it at higher strain and I don't have any failures, that's the better I get for cracking. This is the soft binder with the low amount of wrap, recycled material in it. Here, this is, the blue one is the low recycled binder content with the stiffer virgin binder. Now here we see this particular one is the soft virgin binder with the higher percentage of recycled material. And then this particular one on the bottom here, this is the yellow one, is the stiffer binder with the higher percentage, right? So this test is more in line with the binder properties. You know, the more wrap, the stiffer, with the stiffer base binder has the less performance. But again, fatigue is usually now, it's not a fracture crack, you know, maybe top down. So IFIT is maybe more related to top down, overlay test more to top down. This is thickness, had you know, millions of load applications and deflections in the pavement. And to tell the truth, depending on the thickness of your pavement, this could still work okay if your pavement is very, very thick and I have very, very low strains. However, I might have more top-down cracking because I'm still going to have relatively high tension at the edge of that tire. So again, you know, these are all things we can do to evaluate the mixes, but none of them are easy. You still have to do thinking about what type of issues you have on that pavement and what are you going to do to address that in your mixtures. We also had thermally stress restrained specimen tests, and that's the one I told you where we take the specimens and we cool them, restraining the ends and see how they crack. And here, for low temperature, if you're, you know, the softer based asphalt with the low bitumen content, the low recycled bitumen content, because it had the lowest temperature. And as we went to the higher recycled bitumen ratios, with the stiffer materials, just a little bit worse. But and these are all aged also. We age these to again, because low temperature cracking is an aging condition. So we looked at that and said, okay, you know, they start to come back together for cracking. All right. Well, I got to look at my time. See, okay, I'm on slide 40 of 79, and I got half an hour left. So, but that's okay. We'll get through, and I won't speed it through. We'll address the most critical things to look at, and I'll show you a couple of other different mixtures. And this was a different study, and this particular case, this was a study looking at polymer and the effect of polymer on cracking. But we also had two different base bitumens that we were dealing with. One that we knew was sort of a base bitumen that had poor cracking properties, and one that had good cracking properties. And we wanted to see the effect of the polymers on the two different bitumens, ones that we knew were sort of good and one that wasn't. And again, looking at the performance test. So here we used just one mix design. So we had 4 different mixes that we were testing. You know, the two without polymer and the two with polymer, but they were all made exactly the same. We used a relatively fine gradation. And then we looked at performance criteria. Okay, and this is the IFIT test, showed you earlier. This is where we had that fracture test, the semicircular bend test, and we look at the post-peak slope and how that crack propagates. And in this particular case, what this told us is that the polymer, because these E grade, this is the MSCR specification. So this is a poor binder with polymer in it, and this is a good binder with polymer in it. And both of these said, and this was done at 2 different temperatures, said that the polymer overcame any problems we had with the poor asphalt. And here, the good asphalt and the poor asphalt done without polymers, and their flexibility index was lower, both of them. So, and this particular test said polymers overwhelm the cracking potential of these mixtures. And if we look at the fracture energies, because we can look at the fracture energies, they're all about the same. They changed a little bit at higher temperatures, but when we went to the higher fracture energy, you get a little bit less slope, and it changed the flexibility index. But now, let's look at the Texas overlay test, and what I just told you about, where we do a repeated load test on a specimen, but relatively high strain. And this particular test, we did see a reversal of the results. Now, this particular test said, no, my poor bitumen, even though it had a lot of polymer in it, still, it was a little bit better than no polymer, but it wasn't as good as the bitumens that we know were good and had better cracking properties. And where at lower temperatures, they're polymer modified and non-polymer modified were about the same, but as we went to a little bit higher temperature, the polymer modified was even a lot better. But you can see now, there's a reversal for two different types of tests. And that's easy to, well, it's not easy to explain. We can explain that. One is a fracture test that we do. We apply, we call a monotonic load. We apply a load to it, and we watch it fracture. And there, the polymer has a bigger effect because it's stretching and not letting that material crack properly very, very quickly. In the overlay test, now it's a repeated load test. And so now I pull in it, let it push it back, pull on it. So when I pull on it, I create stress in the specimen. Now, the good bitumens, they can relax that stress. The poor ones can't. They always feel that tension. So even when I push it back, I still have tension in that specimen. It hasn't gone away because that's the nature of bitumen. It's a viscoelastic material. When I release the load, the stress doesn't go away immediately. It takes time for it to relax. And the faster I can relax that stress, the less cracking I'm going to have. So as I'm pulling back and forth on that specimen many, many times, with a poor material that doesn't relax, that stress builds up in the specimen. It builds and builds and builds, and the cracking happens sooner. And that's what we're sort of seeing here with this. And that's why you see a different type of result. So depending on the type of cracking you want to look at, if you're going to have a lot of repeated load, or if you think you're going to have just heavy loads that you want to deal with, the testing might give you slightly different results. And it's important to know that. So, we have to look at the thing, and look at that in the testing that we deal with. So, and again, the Texas overlay test was more sensitive to the issues we had with the bitumen, with being good or bad, than the iFit test. Now, in balanced mix design, though, you can't just throw away everything you've done in the past. You still have to have your specifications for bitumen. You want certain properties. Hopefully, they're performance properties. Whether it's a multi-stress creep and recovery test, which is AASHTO M332, or whether it's some other type of polymer specification that you might have. You're going to still have to have your basic material specifications to have the properties of both the bitumen and the aggregate that you think will optimize the performance. But then you do the performance test to give you that final balance between the two. So, you don't throw out these specifications. We still have aggregate specification. Here's the superpave end design. Here are aggregate properties based on the amount of traffic. We can maybe make those a little bit more flexible with balanced mix design, but we don't throw them away. They're your starting point, and that you adjust from as you're going through this process. So, what's currently being done, as we talk about in the U.S., there's a lot of different things. When we look at agencies that are actually doing, what we call a full balanced mix design, where they're looking at rutting and cracking tests and trying to optimize the bitumen content with the gradations to get the best performance they can, there are a few number of states that are starting to do that. You have California that's done some work, Texas, Louisiana, Minnesota, Wisconsin, Illinois, and New Jersey. They actually have specifications in place, and we'll go over, what they are. And, there's 3 different approaches to this balanced mix design right now. And the one that is mostly used is, let's do it here. The one that's mostly used, this is just a bigger picture of that one is altogether, is designed with performance verification. And so that's where you do your basic volumetric design, whether it's the Marshall or the Superpave. You go through and optimize those properties. Then you go back and you do performance testing to see if you got the characteristics you want from that basic mix design. And if you don't get those characteristics, then you don't just say, I'm going to make adjustments to my bitumen. What I have to do is go back and redesign the mixes so that the basic, I meet all my basic volumetric requirements, but then also meet the performance characteristics. So that's the probably right now at this point the most predominant approach, and that's because people feel comfortable with that. That's their comfort level. I mean, I'm doing volumetric mix design for the past 50 years, whether it's Marshall or Veeam, Super Pave. I feel comfortable. So a lot of highway agencies are, reluctant just to say, well, maybe I can change those a lot by this performance test. So, but in the end, what we're looking for is to go really to the next step, is to go to what we call performance modified design. And this is where maybe you start with your basic volumetric characteristics. You do your initial mix design. Then you do your performance testing. But instead of going back and trying to redesign the mix to get your volumetric properties exactly back where you want them, no, maybe you'll just change the bitumen content. Maybe you'll adjust, and I'll show you some examples of that as we go along. Then the other one is what we call a purely performance design. And that's really where maybe you start off with just a basic volumetric design, but then you do the performance testing, and you might adjust the gradations, you might adjust the bitumen content, and really, in the end, you really don't pay any attention at all to the original mix design, whether it's Marshall or Super Pave, and you let the performance characteristics completely take over. And that's the one where it allows you to do a lot of different things, but that's the one where people have the least comfort level, because now you're throwing out all your past experience, and no one wants to throw out all their past experience. I mean, it took me a lot of years to get my experience, to get all this gray hair. I don't want to throw it all away. I want to keep some of it. But maybe I might be open to a lot more change than I think. And so we have to, balance, and that's what we call this balancing. So when we look at this, currently, what you see, California has done some of the performance design. They, not a lot. There's just been a few really, really major projects where they let performance testing really run how that mix would be used. It takes a lot of testing, a lot of work to do that, though, and so that's why it's done a lot. Now, also New Jersey has done some of that, not as much. These states, again, we showed you, this is sort of the basic performance. That's where you do your basic volumetric design, and then you make adjustments, and you could change the bitumen content based on the performance test. And so you don't rigidly follow your old design process. You make adjustments based on the performance test. Now, these other states that we're showing here, these ones in sort of a brownish orange, they're states that actually do performance testing, but it doesn't control the design. They might just run the Homburg test to make sure the mix that they design has certain rutting characteristics. And that's the most predominant one that gets used in the U.S. because it's the easiest one to use right now. So you see a lot more of that. But, there are a lot of states that are looking to do a lot more. All of these states, are looking to advance their systems to do a lot more than they have in the past, to go from that just basically checking to doing some kind of performance design. For example, in Illinois, just to give you their example, they have the two tests that they use. They use the Homburg wheel tracking test, and they use the flexibility index test. And again, I told you it's the Illinois flexibility index test, and that's because it was developed in Illinois, and that's why they use that test, because it was developed at the university there. And they have different criteria that's required. You do a basic volumetric design, and then you go and you check your properties and they say, you know, all right, depending on the type of roadway I'm using, whether low volume road or high volume road, and they change the bitumen stiffness for the PG grading based on the amount of traffic. You can allow so much rutting in a mixture after so many load applications. So at very high traffic, where they use a PG 76, which is, you know, usually typically polymer modified, they require minimal, you know, rutting at 20,000 passes. And then they look at the flexibility index, and they have a minimal criteria for that, that you have to meet, whether it's high traffic or low traffic. And so, and in this particular case, if you don't meet this, you have to redesign your mixes. But you know, it's the performance criteria that drive what goes on with that. And so, if you look at it, it sort of looks like this. And if you want to visualize it as a chart. So if I have, here's my flexibility index values, okay, and here's my rutting values. And so here, if you look over here, this is the actual numbers. Okay, here's rutting, and here's the flexibility index. So if I have a minimum value for flexibility index is here, saying that I have to be, you know, above this line to be a good mix. And here's my rutting number for the number of passes. So I have to be on the right side of this. So this is where the mixes all pass. So I'm above my flexibility index minimal value, and I'm below my rut maximum value. So here's where the mixes pass. And everything outside here fails. Now these mixes aren't the same, because I could be here, which means I have a good flexibility index, but I also have a lot of rutting, which I don't want. Here I have a very brittle mix, no rutting, and poor flexibility. And here I have high rutting, maybe a poor aggregate structure, and low flexibility. So, you know, they're all affected. Now in here, just like if we go to here in this example, this is you know, maybe 3 different bitumen contents, and so you can see here, these are the different grade bitumens. There's a 6422, 6428. There's a 6422 and a higher percent of bitumen, 0.4% higher bitumen. There's 6422 with a polymer, and you can see you have certain, you know, they'd all pass, but they're all, you know, slightly different values, but they all in this acceptable range. And this also gives you the contractor or the designer more flexibility on what he wants to do to make those mixtures fall in the acceptable range. I could add polymers, I could add slightly higher bitumen content, I could change the bitumen grade. They all might have some effect on what goes on in that, and so you can optimize for what they want to do. Here's Louisiana's approach, the state of Louisiana. It's somewhat similar, and what they particularly do, they have, they use a slightly different semicircular bend test, just looking at fracture energy in their particular case, and they also use the Homburg wheel tracking test. And depending on whether the size of the maximum size, nominal maximum size of the stone, they slightly change their criteria, and so they have the rutting criteria, the amount of acceptable rut per passes, and that changes depending on where you are in the pavement structure, which is another important thing that we have to look at, is where are you in the pavement structure? Because where's rutting going to happen? Typically. Not always, but typically where's rutting going to happen? At the top, it's going to be in the surface. Where if you go down in the lower layers, the stresses are lower because it dissipates as you go down. And so rutting is usually more related to the surface. And so as I go lower down into the pavement, even though the traffic is the same, maybe I don't have to have as stringent a rutting requirement. But as I get closer to the surface, I do. But again, the opposite is true for fatigue cracking. Now, fatigue cracking, my high strain is going to be the bottom of the layer, and the crack's going to come up. So depending on where you're trying to address your problems, you have to look at how you're going to set your criteria. And then they also have the SEB results, and they require a certain fracture energy at the level, which is a 0.5 JC, which is their fracture energy calculation. So they require that for all the mixtures, because cracking can be from the bottom down, bottom up, or the top down. So they don't vary that based on the thickness. In New Jersey, a very similar type of thing. Again, you do a basic volumetric design, then they do testing with their asphalt pavement analyzer, which is similar to the Homburg wheel tracking test, but then they use the overlay test. That's one they got familiar with. Their agency has used that. They feel comfortable with that test, and they have certain requirements, a number of cycles to failure based on the traffic levels. And that traffic levels, again, also controlled by the binder stiffness. In other words, they use 6422, which is a typical 60-70 pen asphalt, bitumen. That's used on lower volume roads, and then for higher volume roads, they use the polymer modified, which is typically a 76. And so they adjust the number of cycles based on traffic loading. And the same thing with their asphalt pavement analyzer, the amount of rutting that they allow after so many cycles of application of the wheel load over the thing, they vary the amount of rutting that's acceptable. Again, the concept. Now, they are experimenting with allowing no binder spec at all and just trying to control the rut and the cracking with the overlay tester. But that's just some very preliminary work they're doing. With Texas actually allows the contractors to adjust the bitumen content based on the performance type testing. So they do Homburg wheel tracking and their Texas overlay test, and of course, they use Texas overlay test because they're Texas, right? It was developed there. They want to use the Texas overlay test, but they also still have requirement. They have you have your binder grade that they specify, whether it's polymer modified or not. But they also have this performance criteria for cracking, which is with this delta TC. And I showed it to you a little earlier. I didn't get into detail. I just told you good or bad. This sort of controls the cracking properties of the bitumen. So they require that. You can adjust the VMA based on the Homburg wheel tester and the overlay tester. And you do that, and they also do the testing during production. So they have, they do set maximum amount of recyclable limits you can use. They cut that off based on the amount of binder that you replace. Though they don't let you adjust that too much. You can put only so much rejuvenators in there, not just to throw it away, but they have controls over that, and they let you go on. So now here, just to show you what this looks like, the red is the overlay test, and they look at several different bitumen contents and look at, okay, how do I meet my requirements? So here's my requirements for overlay test. So at 300 repetitions to failure, I can get away with maybe 5.4% bitumen. And then here's my rut testing, and I look at this, and I said, here's a 12.5 millimeters, and this says that, well, I can go up to maybe 5.8 bitumen and still be good for rutting. So in between here is the acceptable range for bitumen, because I pass both the overlay test cycles to failure, and I also pass the rutting. So it's going to be in between here. Now, of course, as a contractor, if I don't have any restrictions, I'm always going to give you this lowest number. I have to, because I have to be in the competitive. So sometimes what highway agencies are doing is, just to show you, this is a, maybe I took, okay. You can set your requirements that you have to be in the middle of this range, type of thing. You know, and that's, again, that's up to the agency. You can say, okay, here's my range, and I have to be in the middle of that. You know, that's where I set the specification. Because if you don't, you're always going to get the very lowest value, because that's what the contractor, I have to give you the lowest bitumen content, because that's competitive. Oklahoma is very similar to Louisiana. They're doing the semicircular bend test, the Louisiana version, but they allow, again, flexibility in your VMA, your bitumen content based on that. You know, Wisconsin is doing for low temperature, they use the DCT. At low temperatures, they use the semicircular bend test, the IFIT test, at intermediate temperatures, and then the Homburg test at high temperatures. So Wisconsin is a very, very cold climate. They have problems with thermal cracking very often. So that's why they include also a very low temperature test, because that is a distress they have, and they want to be able to adjust that. And just wanted to get here just so that, you know, we're running out of time. You know, this is, again, a similar type of thing. Here's your bitumen content, and, you know, and here you're rutting as the bitumen, the cracking rather, the cracking goes up as the bitumen content goes down, and then the cracking improves, and then the opposite is the case for the rutting. And so we want somewhere in the middle here where we can get optimum values for both cracking and rutting. And what we can do then is look at this as sort of a cost. You know, how much does it cost when I change my bitumen content? I have increased my bitumen content, I'm going to increase cost. So I have to look at, you know, where am I going to be in this? And I can then optimize this based on cost. There's work now being done as an NCHIP synthesis project, basically to look at setting up, you know, what do we need to do to set up a balanced mix design approach? Because you can't just take someone else's work and adopt it. You can take the concept, but you have to make adjustments. And I'll give you the perfect example. Illinois wanted to follow Texas to a certain extent on their approach. Now, Texas is a southern state. It's a warmer climate, different materials. So when Illinois decided to try, they were going to adopt the Texas, Homburg wheel tracking tests, and they were going to use the Texas specification. Well, they started testing their mixtures, and they found that none of the mixtures they used would pass the Texas specification. And they said, we got problems. We want to use this, but here's a test spec Texas has been using. They say it works for them. We tried their same spec, and it doesn't work. Well, yeah, because you have a different climate. You're using slightly different mixtures, and so it's a cooler climate. So if you try to set the same criteria for Texas where it's warmer, it's not the same. So they had to make adjustments. And that's the same thing now. Anybody that wants to do it, you don't have to reinvent the wheel. You don't have to come up with your own test. But how you set the exact limits are going to vary slightly depending on your materials and the climate you deal with. And that's what this talks about, doing that. So there's a lot of different approaches that are being looked at to address what's going on. And there's work being done to say, you know, how do I address based on the temperature, climate I'm dealing with, the aggregate properties I might have, you know, the wheel loadings and that type of thing, because they're all going to affect exactly how you establish those criteria. So, you know, when we look at, you know, volumetric mix design versus balanced mix design, you know, we see here you have a very rigid requirement, you know, whether it's some kind of volumetric property, that 4% air voids is, you know, that's exactly what you get, you know, and so you have one number, and you're locked into that, whereas with the balanced mix design, you're going to optimize for, say, your cracking and your rutting properties. So, where volumetric might say 5.7 is where I'm going to be for my mix design, if I want to optimize both rutting and cracking, I might find that I actually add a higher bitumen content because I'm now trying to address both rutting and cracking. So if I accept my volumetric design at 5.7, yeah, I'm probably going to have very good rutting properties, but my cracking property is going to probably be very, very poor. But if I go to here, I can fit both and get good, reasonable performance on both. And so that's really what we're talking about with the balanced mix design and performance testing. And I tried hopefully not to make the performance testing too turn you off too much because there's issues. But you have to realize that you have to pick the test that best suits the type of distress you have, and then set the criteria based on your local conditions to do that. And then you can, the overall concept of the design, then you can trust. So I got 2 minutes left, I'll just quickly talk about field acceptance. I don't want to get in the way of lunch. I heard, I know that you don't want to stand between, somebody and their stomach. But when you get to field acceptance, now, because we do all this work in design, and then the question comes about, well, what do you do during production in the field? How do you make sure the contractor is actually giving you what was designed? Well, historically in the past, what do we look at? We look at asphalt content and bitumen content. That's sort of the typical, it's the easiest one. We say, okay, that's what he controls, that's what he puts together, right? So, well, what you find, and that was a study I did back in that case was the mid to late 80s. That's 1980s. A lot of you weren't born yet. There's a few of you that were, but not too many. Is that even though the contractor was providing the bitumen content and gradation pretty close to the job mix formula, when you went back and looked at other properties of the mixture, you found that during that production process, when they went together, it didn't match up what was happening in the laboratory. So that's when we came out with the concept of maybe using volumetric properties. So we actually made Marshall specimens in the field and checked the Marshall properties of the mix that as the plant produced it, did that match the original mix design? And if it didn't, well, you could make adjustments and then tweak the mix so that the Marshall properties of the mix produced at the plant matched then your design. And you might change the bitumen content, change the gradation slightly. And we do the same thing for superpave also. In other words, you design the mixture in the laboratory, you get a gradation and a bitumen content. Then you go to the field to check to make sure that the mix that's produced by that plant gives you similar properties, because just because it gave you the same bitumen content and gradation, no, that plant now is very different in how it treats the aggregate. I mean, and I'm in the laboratory, I take the aggregates and I sieve them out and I recombine them, But in an asphalt plant, I have a big rock tumbler. I've got flames going in there and I'm putting tons of aggregate into the drum and I'm rotating it, heating it, drying it up. I'm knocking off the sharp edges. I'm generating more dust. I'm changing the properties of those aggregates. And so when I put them together, if I try to put them together at the same gradation and bitumen content that I did in my laboratory mix design, I don't always get the same properties. So you need to make adjustments. And when we talk about performance mix design, we have to take into account that same type of thing. So right now, probably the predominant things to do with the balanced mix design, as we go through and we do our balanced mix design, we get all our properties, and then we go back to volumetric requirements. So we say, okay, what are my volumetric properties of that mixture is now I made my adjustments to the bitumen content and maybe a gradation to optimize for performance characteristics. And I say, okay, now when I combine those together, my air voids in the mixture are, now not necessarily 4 for the super pave, it might be 3.5 or 3.6. Okay, that's my new now level that when I go to the field, I'm going to try to reach those volumetric properties in the field. Now, that's still not the best way because, again, we said I changed the mixtures through the plant. I'm going to change the performance characteristics too. So an approach that's being looked at is that you do validation testing again also with performance tests. And then you might have to make slight adjustments in the field to get the volumetrics and the performance tests to be closer to what you want and make adjustments. But so there are several different approaches right now. The most predominant one is just to adjust the volumetric properties to whatever your laboratory mix design was based on, and how that adjusted based on your performance type testing. And you then go back and try to get those volumetric properties as close as possible based on the performance test in the field. So I don't know, what's the typical acceptance here in Costa Rica? For do you use Marshall testing in the field?
Marshall in the field 7% of the air content.
Okay.
Basically, that's it.
Okay.
For acceptance test, we are using also criteria on rotting and fatigue.
Okay.
But for acceptance of the mixing of the mix design.
Yeah. Okay. So yeah, and so again, you can adjust. Yeah, you can adjust again. You do your Marshalls, but you would now target Marshall properties not by some percentage of your lab Marshall, but you would you'd target them based on how those values were adjusted based on performance testing. So now whatever the air voids were, and the bitumen content were based on the performance testing, then you would go back and say, all right, what are my air voids, VMA, and bitumen content based off of the performance testing and how I adjust them, and that'd be my target. And then the other one would be, as they say, is that during the first day of production, you take a sample, you go back and do the performance testing and see how that compares to your original mix design, and then maybe have to adjust off of that. So these are some of the different criteria being looked at to be able to adjust that. And what we see, you can't read this, but I can basically tell you, it's a combination of all those. But again, the most predominant one is just to use the volumetric properties for control, but you can use volumetric plus performance, or you can do just performance. But this one gets very, very difficult because the testing time is significantly longer. Most contractors don't want to wait a week to find out if their mix was acceptable. So again, that's why maybe we do this as validation right up front, but then you go back and really control based on the volumetrics. So with that, what is the future of balanced mix design? Well, we're going to look at trying to refine the criteria more so that you can get a broader based idea of what they should be based on climate materials, instead of having to maybe tweak that for individual highway agencies and states. So with that, I went quickly through a couple of places, but hopefully we do have time for some questions, and I'm more than happy to discuss any of this with you. If you got any questions, comments, thoughts, because for me, I learn from you guys too. Believe me, every time you talk to somebody, you learn something from them. It's important. So, but I'm more than happy to any thoughts you might have.
Actually, Dr. Angelo, pointing out the last slide that you showed, as I mentioned, we have some performance-based specs fatigue and rotting, we haven't touched at all the volumetric properties. So we haven't adjusted anything. And the other thing, one of the contractors had a very bad time trying to meet the fatigue criteria. And as you know, and we know that the contractors don't like to change the job mix formula at all.
No.
Mostly if it's been working well for years. So we have had this issue all this year. And the problem is that it almost caused penalties over a huge penalty. We are talking about $1-2 million for a retention of the payment because they were trying to get mostly the fatigue test. So what are your thoughts about that? Because we can do a research if it is needed about adjustment some of the criteria. The VMA always is tough here to meet the 14% is the normal for our type of mixtures. But the fatigue test we had a pretty bad time with one of them, and I think it's too variable sometimes. Here there are some guys of the lab and from the research and from the auditing group that has faced this thing with the contractors.
Yeah, that sort of mentioned in the beginning is if you try to maintain your original criteria for the marshal, for example, whether it's VMA, air voids, narrow gradation bands, then to try to put performance tests on top of them can be very difficult because it could possibly be that those criteria you had don't really give you the optimum, as you said, maybe in fatigue. Now, the other comment was that, well, those mixes have been working for a long time. And my response to that is that, well, yeah, you used them for a long time, and you accepted the performance for a long time, but it doesn't necessarily mean that it was the optimum performance. Contractors got used to producing a mix. The highway agency got used to the performance they got for that mix. It was something they say, this is what we have, this is what we're going to deal with. And so, and again, that's why I mentioned earlier, that you have to be able to, willing to step outside your past experience to look at something new. Because, as you say, if the contractor doesn't want to change because he's going to get penalized, he says, I have to have my VMA at a certain value. Well, if I change it, I'm going to be penalized, but I can't meet your fatigue requirements, so I'm stuck. And then, but that's what we try to do with some trial projects. In other words, you go and you build a short section, and it might be only 1 kilometer or something, with the new specs that waive not the general requirements for but a waive that it might be some of those more restrictive volumetric specifications you have to show that it does work and it actually improves performance. And that's a key item, especially for the highway agencies, that there's these trial sections to say it does work, because that's the only way you're going to move forward. The highway agencies aren't used to the performance testing; they're unfamiliar with them, so they're unwilling to make the changes. But if you can do a short trial section somewhere to demonstrate that these things are an improvement, it can go a long way to being able to make some of those adjustments.
I have another question. I'm pretty sure that the other guys have questions here, maybe. But another question. We raised up the dose proportion from 1.3 to 1.6 because. Again, some of the contractors were not able to meet the specification at 1.3, and most of them were very close always to 1.3, 1.29. So we do sort of a short analysis. It wasn't like a big research, and we did it following SuperPave because SuperPave allows you to reach 1.6. So it gives me a lot of peace to know that SuperPave allows that. So, but what is your criteria about that? Here there is a lot of people that told us that we are allowing the contractors to put more sand instead of asphalt, and we are producing drier mixtures. So what do you think about that? Well,
I mean, it all depends on the overall gradation that you're dealing with. And I'll go back a little here. For, yeah, okay, I'll show you this. This type of gradation, I'm not sure that, what type of gradation you have here, but I just show you, this is a fine graded mixture that we did in the study now. And a mixture like this one, when you have higher dust percentages, you're going to have a lot of problems because it is going to make the mix very, very brittle and dry. Because we typically see that you have the air voids are well dispersed. You have a lot of thin particles, and you don't have a lot of stone-on-stone contact. But now if I go to a mixture that looks more like this green one here, that's what we found, that you can go to the higher amounts of filler or dust in the mixture. Because now you have the areas where the mastic are, you have larger stone, you have stone-on-stone contact, and you're starting to fill in the voids between the stone with a mastic, which is the dust. And we find that these work quite well. Matter of fact, they actually work better with slightly higher filler contents because you have typically, as I showed you, this particular mix, this green one, had a little bit lower binder bitumen content, but it actually had a higher volume of binder. And so you actually can put a little bit more filler in there to stiffen that up, and it works quite well. So it's not just one answer, yes, you can use it, you can't. It really depends on the type of mix. Like stone mastic asphalt. Those mixtures are very, very coarse. That stone mastic asphalt mixture we have a gradations down here, then jump up. And there we look binder to filler ratios of 1.9. But again, we have a little bit higher volume of bitumen, and you want to stiffen that up. And then it's not, that filler is not getting in between all these small little particles that don't make content then. It's filling up voids in the bigger stone. So you have bigger stone making contact, and you fill up out those voids with the mastic in the stone. And so you have to look, as again, there's no one answer. You have to look at how is it going to react in the type of mixes I'm using. And I said, I don't know if you use typically fine graded mixtures or coarse graded mixtures.
Mostly fine.
Yeah, okay. So, but again, you have to look at the shape of the stone and everything else. So, and again, that's the key to the performance test. I would go to is that filler content causing those mixes to be brittle? Is it causing problems? That would be the key to look at. Whether, and I would probably look more on which fatigue test are you using?
4-point Benjamin.
4-point Benjamin. Yeah, for that I would probably maybe look at maybe it'd be the iFit test or the overlay test to see if I'm getting like poor fracture properties because of the high fillers.
Very good. They have another question regarding the fatigue test. It's pretty good to know that all the various states have their own specs. How do you, about the various ways of compacting the samples, the effects of that? Some people use them, like a static, others use rollers. So what do you recommend about that?
Maybe I should let Joe handle that one. She's got a whole study going on that now. What we want to do is try to simulate the field as much as possible, but that becomes very difficult and very, 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 very complex to do. So, but what we've seen is that any kind of slab compactor works reasonably well, but you're going to have to get that transfer function to what you typically see as acceptable for your region is going to be affected by how you compact your specimens. I mean, if I compact it with a a big mold with an actual roller, or I have a slab compactor, or it's either small or large, I might have slightly different results. But once I establish what my acceptable criteria in relationship to the roadway, that's where I'm going to have to make my adjustments based on that. But but there are several good approaches now to do that. There are several of these small slab compactors that have a steel plate that compacts the specimens. There's also the ones that they have the multiple plates that a roller goes over the top and just sort of pushes down, trying to simulate it. They all work reasonably well, but nothing's perfect. The best thing would be to cut slabs out of the roadway, but no one wants to do that.
¿Alguna otra pregunta para el doctor Angelo?
You talk about the variability in the test, well, in all the performance tests, and I want to know your opinion about the fatigue or the cracking test, because you show like 4 types, right? Really, and in the specifications, I noticed that they have they use a lot the overlay test, but here we use the fatigue test that is with the beam with 4 points. And we have a lot of variability in that test, and that one of the issues when the contractors that Guillermo tell the first question about the problems with the contractor, one of the issues is that they talk about the variability with that test. So I want to know, with your experience, if you say that is one test better than other in variability.
Yeah, there are tests that have less variability than others, but any of the cracking tests, just by their nature, when you try to fracture something or break something, you have significantly higher variability, and so the best way to handle that, especially with the contractors, is to establish, and it was sort of mentioned in the slides there. You establish what that range of variability is in the test. And so if I know that I have, 30% variability, well then I can say, okay, within acceptable range now, based on that test result, I can accept, within certain limits, plus or minus from my design, and you can, and so that's the most predominant way to do it, is to establish what those variability limits are, and then try to go back and say, okay, when I test some other materials, am I within that range from some target value I have? But when you go back and you look, there's been a lot of work on variability of all the tests, and I know. For like the beam fatigue test, there's been quite a bit of work now. There's a new ASHTO specification that's trying to reestablish, instead of just looking at the 50% loss in modulus as your failure, is looking not so much just at that, but it's actually looking at the increase. Increase in loss and modulus with cycles, and so that it becomes a little bit more, a little bit less variable on just looking at the modulus. But and I think that's actually helped quite a bit to reduce some of the variability. So there's work being done on actually how you set those criteria that reduces some of the variability. And I think same thing with the Texas overlay test. It's considered a very, very highly variable test. But Texas now has looked at some different approaches on how to analyze the data to significantly reduce that. So I'm not sure which exactly approach you're using now on the fatigue test. If you're using the older ASHTO or ASTM, or the newer ASHTO. But the newer ASHTO supposedly dramatically improves that analysis and reduces the variability. But The other option is to say, okay, what is my variability? So if I have a 30% variability and I know that, okay, I want, 100,000 repetitions at a certain microstrain, and I say, okay, my variability is 30%, well, then I have to accept maybe, 70,000 as an acceptable test result. So they say, okay, you say you're worried about variability. Well, I allowed you my variability. This is my variability. I know what it is, and I allowed you to be within that range. And if you tell them up front about that, then most contractors are pretty sharp people. They can, and especially when it comes to things like analysis of risk, that's what they do on a daily basis. So they can understand risk, and so if you let them know that the risk is reasonable and that you consider that risk, then sometimes but now, to tell you the truth, if I'm a contractor and my things fail, the first thing I'm going to do is I'm going to tax something. So yeah, that's a good thing to tax. But if you have a good answer to say, well, up front we've discussed this. This is the variability, and we've taken this into consideration. It makes it a little bit more difficult for them to use that argument, but they're still going to use it.
Hi, sir. I have a question regarding the specification limits. Based on your experience, for all these states, for example, that they develop, let's say, an IFIT criteria or Homburg or overlay, they have a wide range of data. So generally, from all the samples they test, from all the mixes, they go like for a 50% to set the limit, or they're more conservative, maybe a higher percentile or a lower value. How do they set this value?
Okay. Yeah. The typical process is to go back and you test. Again, you go back and take samples from a lot of existing construction projects, or actually take cores out of the roadway that you know some performance characteristics for. And then you do a normal statistics. You draw a bell curve for that, and you say, all right, these are the mixtures that performed well. These are the ones that didn't. Where does that criteria then fit? And then you do have to look at that variability, and you look at, I might pick for my lower limit, the 50% reliability criteria for, say, that's the lowest limit I'll accept. Or if the other approach is to say to pick the 85% reliability value, and then say I want everything above that. Now, you're going to force people to make more changes that way, but sometimes you can start with the 50% reliability as your limit, and then as you go on, and see how the testing goes, and you can adjust it in a tighter range as the industry gets more familiar with that value. So it's very, very, very common to set it at about a 50% reliability and then adjust it up as you go, just so that you get people the opportunity to get familiar and used to the values. And you can do this in a trial phase, in other words, the specification doesn't happen all at once. You might do 2 or 3 trial projects one year. The next year, you do a few more trial projects. And eventually, maybe over a 5-year period, you switch from 0 projects to 100%. And then after that time period, the contractors are starting to get used to it. And then then you make adjustments to those mixtures as you go. So it's always a political and scientific thing. It's never a straight, direct answer, because you have to get people comfortable with the ability, one, that they can produce the mixes and get them down, and then also that you're going to get improved performance. And so what we find that's typically the way it gets adjusted. And that's very common in the U.S. is to do, you know, the highway agencies to do several trial projects over a number of years to get everybody adjusted to that.